Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the granulator. First, let us understand what's a granulator, what is its purpose, and how does it function. Granulation is a process in which the smaller size powdered particles, they bind together with the help of some binder and then they form bigger size granules. You can think of a situation where you have a pile of wheat flour, and if you sprinkle some water onto it, then you will find the water droplets will catch those wheat flour and small globules will be formed. That's exactly what granulation is. Usually, granulation takes place inside a vessel of this nature, where you have an inlet of seeds. Seeds means the smaller size powdered particles which are destined to be granulated. And those seeds or those granules will come out of the vessel through some stream which we'll call wet grains. Because if we use a binder material which is usually liquid, then it will be wet. So wet grains will come out. And you will have binder material, and this binder material will be sprayed from the top, which will fall onto the heap of the powdered. And we will have another input, which is hot air, and this hot air will come out as off gas. Now this hot air serves several purposes. First of all, hot air fluidizes the entire bed of these particles. Because if the fluidization happens, then the granulation takes place in a better manner. Secondly, this dries up the granules, because obviously the granules will be wet and due to the presence of binder. Now if it is highly wet, then it will be sticky, but we do not want that. We want the granules to be free flowing, so we want to dry up by removing the extra amount of binder which is present over there. So this hot air serves that purpose. And thirdly, it carries off the extra amount of powdered material which has not taken part in the granulation process. Suppose you have put 1 kg of powder. Obviously, the entire amount of powder will not be granulated. There will be some powder left which will not be granulated, and this should be removed from the system so that we have only granules in the system which we can take it as product. Okay, so hot air carries off that extra powder through the off gas, and it is called elutration. Okay. Now, in order to understand this process, let us go to the Aspen Plus window and see various ways in which we can model a granulator. So this is the Aspen Plus window, and you will find the granulator over here. This is under the model palette. You will find the solids tab over here, and you will find the granulator in this location. So we can bring in the granulator from here and put it over here. And if we choose material, then you will see that we have only two streams that are compulsory. You can see red mark only for 2 streams, one inlet, one outlet. So let us take this out. And this one as we shall call them seeds and wet grain. Okay. Now there are usually 3 methods by which the granulation calculation happens within the granulator block. The first way is by specifying the particle size distribution of the outlet. That means we tell the granulator block that you fit the condition, but I want the particle size distribution of my product to be like this. Then the granulator will do the calculation accordingly. So you do not have to give any information about the binder, any information of the hot air. Nothing is required. Only the seed material and product material, their particle size distribution will be enough. So that's exactly why the minimum number of streams required for the granulator block is only 2. Another 2 methods are by granulation model, and number 2 is agglomeration model. Now these 2 things we will discuss in detail. So suppose we rename it as so this is granulate block. If we open the input specification for the granulation block, you will find that only option for us which is open is specify the outlet particle size distribution. The other 2 options, that is particle growth by granulation and particle growth by agglomeration, these 2 options are not open for us because we have not given any information of the binder and hot air. Okay. So if you want the calculation to happen in that way, then you have to give the particle size distribution over here. You can either specify the distribution function. You know various distribution function that you have learned before, GGS, RRSB, log normal, normal, this you have already learned. So you can give the distribution function. For that you have to specify the distribution function, selection parameter, etc. Or else you have to specify the particle size distribution of the outlet. Now for that you can choose the normal particle size distribution the way it has been defined previously. If your particle size distributions are within the range of 0 to 200 micron, then you have to specify what is the weight fraction of the particle that falls between 0 and 20 micron. So the weight fraction you have to give. For 20 to 40, what will be the fraction, etc. So you have to basically fill up this so that the outlet particle size distribution is specified properly. Then the calculation block is done. You can run the simulation. Right? But as I said that by doing so, you will not be able to do any calculation on the basis of granulation or agglomeration. So for getting these two options open for you, you need to supply the binder material. Okay? So let us add one more line in the flow sheet. That is for the binder material. So we add another material stream over here. And that material stream is let us name it as binder. Okay. The moment I connect the binder stream, you can see both of them are open for us, both of these options. So let us choose the particle growth granulation over here. So this is the first model that we will discuss. Here, the first thing that we have to specify is the cumulative bed mass. Cumulative bed mass means the granulator vessel will have the particles, that is smaller size particles, as well as the granules that has been formed due to granulation. So these are the major portion of your, and also the binder material will also be there. So the entire bed mass has to be specified over here. Okay. And then the calculation model, you can see the calculation model, there are two options for it. One is mixed and plug flow. So this is the mixed granulation model. And this mixed granulation model you will find over here. There are a set of assumptions that are there. On the basis of those assumptions, the general population balance of the particle system takes the form of this. Okay, here n is the number of particles that will be formed, and this factor G is something which will be different for different types of model. Now, there are three types of variations that we'll look for. There will be surface proportional growth model, volume proportional growth model, and diameter proportional growth model. So, three growth models are there. Now, let us see what they are. So, when you have surface proportional growth model, then G is equal to this equation where ms dot is the mass flow rate of the solid, rho s is the density of the solid, and A bed is the cross-sectional area of the bed. So if you supply those information, then G will be calculated, and this will be for surface proportional growth model. Similarly, you have two other cases. These are volume proportional and diameter proportional. For volume proportional and diameter proportional models, you have to use these two equations. So this is for volume proportional growth and this is for diameter proportional growth. GI for both. Here you will find two indices. One is I, another is J. Both of them refer to the size class in which the diameter of the particle falls. For instance, If it is from 0 to 20, then the size class will be 1. 20 to 40, it will be 2. 40 to 60, it will be 3, and so on. The interval might be different for different cases, but that's exactly what we mean by size class. And this size class will be different for the inlet particles and outlet granules. Outlet granules will obviously be of higher size. Okay? So in this case, I refers to the outlet and J refers to the inlet. So here, VPJ denotes the volume of a particle belonging to the particle size J. So you can sum up all the volumes of particle size J and you multiply with rho s, that is the density of the solid, that will be in the denominator, and 3 will be there. And the numerator, you have dpj, that is the diameter of particle of size class J, and ms, it is the mass flow rate of the solid. So if you know all those things, then GI will be calculated. And the next case is diameter proportional growth, for which the same thing will be done for dpj and nj. Okay, and other things will be same. So that will be calculated for GI. So whatever the value of G, that has to be multiplied with the factor which is called the adjustment factor. Okay, growth rate adjustment factor. By default it is given as 1. Now if you have more information about the growth adjustment factor, like it may be 1, 1.5, 2, whatever the information that you have to provide, and ultimately you will get the value of G star. And this G star is the adjusted growth rate, is then used to solve the population balance given in the first equation. So what is the first equation? First equation is whatever we have started from. This is the first equation. So in place of G, you use G star. So that is how the mixed granulation model calculation is done by Aspen Plus. And the next one is the plug flow. Now plug flow model is this one. So this is the plug flow granulation model. Here also you have to have this set of assumptions like before. And the equation is dVk. dVk is the increase in volume of a single spherical particle. So this inside area, this is Vk, and the increase in size, that is dVk. So we have to find dVk by using this particular equation. Now the procedure of calculation is given over here, and this is the mean residence time of a particle that is needed to grow from size dk to dA. dk is the inlet particle size diameter and dA is the outer particle size diameter. Now it is understandable that as long as a particle resides inside a granulator, it will grow in size. So mean residence time of the particle is calculated by this equation, and dVk is integrated for that time duration Ta in this fashion, and the final volume and final surface area can be calculated in this form. Okay, and you can find out that the final value of the volume or the surface area depends upon the inlet diameter and outlet diameter. That means if you choose the plug flow calculation model, then you do not need to supply any more information. You have the particle size distribution of the inlet and the particle size distribution of the outlet. If you specify them, then dA and dK will be specified automatically, and these values will be used for doing these calculations, right? So this is the plug flow model. And now the growth agglomeration model. In growth agglomeration model, first you have to specify the cumulative bed mass as before. And then we have to pass some information about the agglomeration kernel. For that, let us go to the mixed agglomeration model. So in mixed agglomeration model, again we have to have a set of assumptions, and after that the model is based on, this is the model, okay, where pictorially it has been described. This is the U, that is the size of small particle, and this is V, that is the size of the granule. So V minus U, that is the increase in size of the particle, okay. Now this is the agglomeration rate, beta, which is a combination of two factors. One is beta naught, another is beta UV. Obviously, beta UV is a function of U and V. So there are 8 of such kernels. Now all those kernels, they depend upon the sizes U and V. Based on the kernel you choose over here, this is size dependent agglomeration kernel. Now by default it is constant kernel, and if you use sum kernel, this is U plus V. Product kernel means U multiplied by V. Coagulation kernel means this is the coagulation kernel, and so on. So this is how the size dependent part is given. And as we remember, we have another part which is not size dependent, which is time dependent. That is beta naught T. Its unit is 1 by R. Now if it is a constant kernel, then you can specify over here. But if you do not know, if you want the Aspen plus software to calculate this kernel for you, then you have to give certain extra information for that. So you have to choose this determine prefactor, and here you will find 3 options open for you. First option is the superficial gas velocity, the second A prefactor and B prefactor. This is the equation. Fn star is the scaling parameter which uses the information MB. MB is the spray rate, that is the binder spraying rate, kg per second. Rho P is the solid density, that is the particle density, and US is the superficial gas velocity. So that superficial gas velocity you have to feed in. And A and B, these are the prefactors. They are mentioned over here. By default, it is 6 into 10 to the power minus 5 and 1.2411. So these are the default values. If you experimentally found some other values, you can give. And this is the way you find out the beta naught T kernel, that is time dependent kernel. Now you may notice that this illustration option is not open for us till now. This is obvious because we have not given any hot air supply to the granulator model. Next, we will feed in some hot air and check what happens. For that, we go back to the flow sheet, choose materials, and see two options are open. This is gas optional, and this is also optional. So gas in, gas out. We can rename them as hot air and this is exit. Okay. As soon as we attach these two streams, you can see the illustration options are open for us. And one more thing that you may notice, that as soon as we have given the flow, inlet flow rate of hot air, then this superficial gas velocity option is no longer open for us, because superficial gas velocity will be calculated based on the hot air option that we have given. Previously there was no hot air, so superficial gas velocity option we had to provide. So this is the information. But right now we do not have that option at all, because we have given the information of hot air, so it will be calculated by the system. Okay, now let us go to the model. This is the granulator elutriation model. The function is this, where alpha is the measure of separation sharpness, which you have to provide over here, and the cross-sectional area of the bed also you have to provide. V naught is the gas volume flow that has been already given by the hot air feed. So V by A will be calculated, which is Vg, and Vg is equal to V cut, which will be given over here. And Vsi is the settling velocity of the particle Vsi of the classification within the class size I. Okay, so based on this information, granulator elutriation model will function. Okay, so that is how the calculation inside a granulator model happens. Now let us solve a problem.